So we're looking at the nature of the second derivative. We've already been introduced to the concept of the second derivative. So now I'm going to explore how this is useful and what it really is representing in terms of our Cartesian plane and graphs. So let's first look at the first derivative and use the language for first to apply to the second. We know that when we find the first derivative, then we're finding the gradient function, and that gradient function allows me to find the gradient at specific points. At this point the gradient is positive. Over here we know the gradient is negative, and we know that here the gradient is 0. So there are cases. I want to use a specific language for this. So let's look at case 1. In case 1, the gradient is negative because the function is decreasing. So f dash x is less than 0 because our function is decreasing. In section 2, which is a unique point, we know that our f dash x is equal to 0 because my fx isn't changing, it's stationary. No change, stationary. And we know that in section 3, f dash x, that would be here, is greater than 0, and that's because my function is increasing. So essentially these relate. This less than 0 represents a decreasing function, greater than 0 represents an increasing function. So when we find the second derivative, then we are looking at the change in the derivative function, the first derivative. So the same thoughts apply. Let's look at this situation. So the blue graph is what I'm working with, that's my function. And I have a tangent drawn at this red dot. And we can see that the tangent is sloped positively. The graph is increasing. My original function, we hit 0, and then the graph starts decreasing. The graph continues to decrease until we hit 0, and then the graph increases. So we know that the gradient in this middle part is negative, and in the end part it's positive. So what does the second derivative tell us about this graph? And by the way, the red graph here is the derivative function's graph. So you can see at this tip, which is hard to get to, the gradient is 0. At the other turning point, we have a 0 gradient as well. So let's talk about what's happening with the changing gradient. The gradient is positive, but let's use those increasing, decreasing words. Over here, the gradient is positive, and it's a really large number because it's a very steep tangent. And you can see on the red line, the red graph, I am slowly moving down as we get closer to this turning point, to this stationary point. So what's happening to the gradient? The actual value of the gradients are decreasing. It's going from a really large number to a smaller, 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 smaller number until we get to 0. I'll try to get 0. There we go. So we start with a really large number and we move down until we hit 0. So its values are decreasing. And then it continues to decrease. it's still decreasing, it's still decreasing, it's getting negatively larger, if that makes sense. At some point, it has to start increasing again. So from a negative large number, it's going to have to start heading back towards 0. And then it's going to continue to increase towards a very large number. So we're looking at the gradient, we're not looking at our function, what's happening with the changes in the gradient. So, second derivative represents this idea of increasing in gradient, decreasing in gradient, increasing in gradient. Now let's talk about what's this other red dot that's appearing. So our tangent over here, it looks like it only touches in one place. But the reality is the tangent, even though it's tangent to one part of the graph, it's actually intersecting in another part of the graph. And what you notice is, at a specific point, these 2 points coincide. And you can see that the tangent is not quite a tangent anymore. It's a tangent on this side, and it's a tangent on this side, but it's actually intersecting and going from one side of the graph to the other. That's a very unique point. That's where my gradient changes from decreasing in value. So we've started with positive, gotten closer and closer to 0, so it's getting smaller, and then we're going into the negative range, and it's getting smaller and smaller and smaller. And then at this point, it starts increasing. And that point is significant, and we're interested in that point. Okay, so the second derivative shows this change. Let's have a look at the graph of the second derivative. Well, actually, let's look at the tangent to our gradient function. So if you look at the gradient of this tangent, over here, the gradient is negative, right? The tangent is moving downwards. Negative gradient all the way to this point. And then, at this point, the tangent becomes horizontal. At this magical point, the tangent has gradient 0. And then the tangent has positive gradient. Here's, in green, second derivative function. Let's move that tangent, and you can see the second derivative is negative in value, hits 0 here, where we expected it to be 0, and then positive. My red dot is coinciding with this 0, is coinciding with this minimum point for this derivative function. So the second derivative is negative for this section of the original function, where the gradients are starting in positive, but they're actually decreasing, and it's positive where the gradient function values are increasing. Even though it might start negative, its size is getting bigger until it hits 0 and gets to the positive. We call this part, the first part, concave down, and we call this part concave up. And the point where that concavity changes, we refer to it as point of inflection. So let's make the same statements as we did before. I'm going to divide my graph into 3 sections. Section 1, the magical point section 2, and on the right hand side section 3. In section 1, my second derivative is less than 0. remember the gradients were decreasing. You can see if I draw a tangent here to the gradient function, then the gradient of this tangent is negative. So second derivative is negative, and that's because the gradient function is decreasing. At point 2, my second derivative is equal to 0, and that's because there is no change in gradient function. It's stationary. And in section 3, the second derivative is positive because those gradient values at these points are getting greater, bigger and bigger and bigger, because f dash x is increasing. And as I said before, this is referred to as concave down. This is referred to as concave up, and this is the second case is referred to as point of inflection. So what does all of this look like? When we have a curve that goes like this, then even though the gradients are positive, they are reducing in value. The gradients are getting smaller and smaller and smaller. So in this case, we know that f dash x is positive. We know that the gradients are positive, but they're getting smaller in size. They're heading towards 0. So the second derivative is negative. Remember, if they're getting smaller, then the second derivative is negative. Just like if my original function is getting smaller, then it's moving downwards, the gradient function is negative, as I've drawn here. If that's my function, then my first derivative, because the values are decreasing, it's negative. The second derivative is also negative because those gradient values are still getting smaller and smaller and smaller. Negative 10 is smaller than negative 1. The next case is a graph like this. Now we know that f dash x here is negative, but f double dash x is greater than 0. You can see that the gradient values are heading from a negative, large negative value towards 0. So they're increasing. And here's my other case where f dash x is positive and f double dash x is positive because those gradient functions are moving from 0 towards a larger number, so they're increasing. And finally, we have that point where we move from a positive second derivative to a negative second derivative, and f double dash x ends up being 0. Here we can see that f dash x is negative because the function is decreasing. Alternatively, we could have a situation where our f dash x is positive and f double dash x is 0. So there are our points of inflection. We're changing from a concave down, let's do it in a different pen, concave down to a concave up. Here we're moving from a concave up to a concave down, and there are actually 4 of those. There's also this case and this case where we're moving from a concave down to a concave up, and a concave up to a concave down.